Hi everyone, Mr. Bowman here, and we are back for the last activity in Chapter 3. And in this activity, we're going to address a couple of topics. One of them is computer output. And basically, computer output is one of those things, it's a holdover from days gone by where people used computer output that didn't have a very nice graphical user interface like apps on your phone do today. So, not sure why, but the College Board decided back in 1997 when they wanted to give the AP exam that it was important that students knew how to read this. So what you're looking at here is computer output from two different software programs that are pretty popular, one called Minitab and one called JMP. And they're both for regression, relating one variable to another, and I'm not exactly sure what those variables are, but it doesn't really matter so much for our purposes. What I want to do is I want to highlight some of the important information here. You can see that some of that stuff is already highlighted. I want to talk about how you can recognize it. So if you think about a line of best fit, y hat is equal to ax plus b. Y hat is the predicted response value. A is the slope. X is the explanatory variable. And b is the y-intercept. When you look at computer output, A and B are considered coefficients. And that's why this label is up here. B is the constant coefficient. So when you're looking for the y-intercept, you will look for the row that says constant, the column that says coefficient, and you will find the y-intercept underneath that. A in our line of best fit, y hat equals ax plus b, is the coefficient of the explanatory variable. So again, you're going to look in the coefficient column, but the label over here on the left underneath where it says constant, actually let me label that in blue, is the explanatory variable, and the number in the coefficient column is the slope. And you will see that that's very similar down below in the JMP output, except they call these the estimate column. So they do a better job of labeling these as the intercept. So there's the y-intercept, and they don't call it the slope, but they do tell you effectively what the explanatory variable is here, which is any A change. There's a lot of other information in there. The stuff that we're most interested in right now would be things like S, the standard deviation of the residuals, R squared, which is the linear correlation coefficient squared, aka the coefficient of determination. And you will also see that in the JMP output. They call it R square. It's over here. In Minitab, it's given as a percent. In JMP, it's given as a decimal. Root mean square error. Boy, that's a complicated way of saying S. If you want an explanation of what root mean square error means, let me know and I'd be happy to explain that. So those are a couple of examples of computer output for linear regression. You have seen some of that for descriptive statistics. You will see more of it when it comes to inference second semester. So here's an example, and it relates BAC, or if you read this, blood alcohol content. That is the dependent variable in this case, or the response variable. And the explanatory variable, if you look at the table down below, is the number of beers that somebody drank. And that means that the slope is 0.017964, and the y-intercept right above that, I'll highlight it in blue, is negative 0.012701. So we've got a bunch of information there about the relationship between predicting blood alcohol content from the number of beers that somebody drank. R squared is 80%, or 0.80. S is 0.02, and the degrees of freedom actually is 2 less than the sample size when you're talking about lines of best fit, and you could actually verify that by counting the points. We also have a scatter plot, and we have a residual plot, so we can use that to answer some questions. What is the equation of the least squares regression line that describes the relationship between beers consumed and blood alcohol content? Well, hopefully you would say that the predicted blood alcohol content is 0.017964 times the number of beers minus 0.02701, and write it down something like that, or write it down as y hat is equal to the slope times x minus 0.012701, and define x and y hat. Now you're supposed to interpret the slope in context. So in context, what this means is that as the number of beers that somebody drinks goes up by 1, the blood alcohol content is predicted, is predicted to increase by 0.017964. Another way of saying that, if you prefer, is to say the average increase in the response variable, blood alcohol content in this case, is 0.017964 per beer or per additional beer that's drank. Find and interpret the coefficient of determination for these data. Remember, you have to interpret this stuff in context. So, R squared was 0.80. We can say 80% of the variation in blood alcohol content can be predicted by the least squares regression line. That explanation would get you full credit. What is the correlation coefficient? The correlation coefficient is the square root of 0.8, but you do have to pay attention to the association. Is it positive or negative? In this case, it's positive, so we just have to take the square root of 0.8. But if it were a negative association, you'd have to take the square root of 0.8, and then you'd have to put a negative sign in front of it. So what does this correlation tell us? It tells us that this linear association, and we don't know it's linear by looking at R, we know it's linear by looking at the scatter plot and the residual plot. This linear association is fairly strong and positive. The standard deviation, S, is 0.02. That is the average error in our predicted blood alcohol content, and it is 0.0204. Now, I think it's important to think about that in context. So, if you look at, let's say, the average blood alcohol content for this experiment, it's maybe about 0.06. An error of 0.02, well, 0.02 is a third of 0.06, so that actually seems like a fairly big error in the context of this problem. And as you can imagine, I bet that's due to various factors like how much people ate before this experiment, or body weight, and things like that. Is a line appropriate model to use for these data? Yes, it is. Number 1, the scatter plot is linear. Number 2, the residual plot shows no pattern. R is relatively high. R squared is relatively high. S is a little bit high as well, which would say that it's not such a great model, but it's a linear model nonetheless. Letter G, what is the predicted blood alcohol content reading for a person who consumed 9 beers? Basically, we're taking the least squares regression line, we're plugging in 9, we're multiplying it by the slope, subtracting the y-intercept, and it's predicting a blood alcohol content of about 0.15. Not surprising, that's about twice the legal limit, but 9 beers is an excessive amount of drinking. How many beers would need to be consumed for a predicted blood alcohol content rating of 0.25? So to put this in context, this would be 3 times the legal limit. So in this case, you're given the predicted value and you're solving for the number of beers in the least squares regression equation. And if you did that, it would be close to 15 beers. All right, we want to talk about two more ideas, even though we've touched on these prior in this chapter. We want to talk about those two ideas one more time before we wrap this chapter up. And the first one we want to talk about is this idea about outliers and influential points. And so what you're looking at here is the age of 21 children in months that they spoke their first word, and a score on an aptitude test called the Gesell Adaptive Test. So in this case, we are going to look at the age at first word in months as the explanatory variable and the Gesell adaptive score is the response variable. And what you can see for the most part is that there's a relatively strong negative linear association. In other words, the older the child was when they spoke their first word, the lower their score was on this aptitude test. Now there's two children that I want to focus on in particular, child 19 and child 18. And I think we would agree that child 18 is both an outlier in the horizontal and somewhat in the vertical direction, while child 19 is not an outlier in the horizontal direction, but is an outlier in the vertical direction. In other words, they had a much higher score than every other child, but the age at which they spoke their first words was pretty common. What you're looking at here is a residual plot for the age at first word and the Gesell adaptive score data. And what you can see here is that child 18 has a pretty low in magnitude residual. In other words, that point falls close to the line of best fit. Child 19, on the other hand, has a relatively large residual. And you can also see that child 18 is an outlier in age at first word and not in terms of the residual. Child 19 is an outlier in terms of the residual, meaning their adaptive score was much higher than most of the other students. Clearly, in terms of this data, child 18 and child 19 stand out and as such are called unusual observations in terms of the data. What we'd really like to know, though, is other than both being outliers, which one has the most influence on the least squares regression line? And so what we're going to do is we're going to open up a file called the Gesell file, which is basically this data, and we're going to manipulate those points to see what happens. Before we take a look at this data dynamically, I want to remind everybody, we already know what an outlier is. It's an unusually large or unusually small value in a distribution. And in the case of two variable quantitative data, it could be an outlier either in the horizontal direction, X direction, or in the vertical direction, the Y direction, or both. So what we're going to do is we're going to take a look at this Gesell data, and we're going to look at the least squares regression line with child 18 removed, with child 19 removed, and we're also going to look at the value of R squared. An influential point is a point that when we remove it from the data, it has a dramatic effect on the least squares regression line. Now, what dramatic means, I don't have a definition of that. Okay? However, you'll know it when you see it. So here is the least squares regression line with all of the data, and you can see it down here. It's kind of small, but down at the bottom by my cursor. And we have a slope of negative 1.13, a y-intercept of 110, and an r-squared value of 0.41. Well, we are going to remove, let's see, which one do we want to remove first? We want to remove child 19, and child 19 was this child right here. So we are going to take them out of that. We'll call it deleting the case. And you can see visually that the least squares regression line did not change a whole lot. R squared did go up. It made a relatively big impact. Removing that point made this association stronger. But now we're going to put that point back and remove child 18. So here we've put child number 19 back, and now we are going to remove child 18. So I've highlighted child 18, and I'm going to delete that. And you will see that not only did the slope change pretty drastically, and it's a little hard to see in the graph itself, but if you look down here at the equation, it changed pretty drastically, but so did the value of R squared. It dropped much more than when we removed student or child number 19. So the conclusion that we make from this is that child 18 was not only an outlier, but they were an influential point. And child 19, the one up at the top there, was an outlier in the vertical direction, Gesell score, but not an influential point. And the takeaway from this is that not all outliers are influential points. The outliers that tend to be influential points are the ones that don't fit the pattern of the data so well and are outliers in the horizontal direction. And to make that real obvious, I put child 18 back, and now I'm just going to take them and move them around a little bit. So again, you can see the original slope and y-intercept and R value. And I am going to move them around. And so child 18 now has a very high Gesell score, but also a very high age. It's not fitting with the pattern of the negative association. And what you see is that the R squared value has dropped significantly and the slope has gone from negative to positive. So outliers in the horizontal direction that don't fit the pattern of the data are influential points. Now I'm going to take child 19 and I'm going to move them around a little bit. And you can see I'm moving them quite a bit, but it's not having a huge impact on the value of the slope or the value of the coefficient of determination. So that is the takeaway from this activity. Outliers in the horizontal direction that don't fit the pattern of the data tend to be influential points. Outliers in the vertical direction are outliers, but they tend not to be influential points. And we are going to wrap up chapter 3 and this activity by talking about association versus causation. When we are talking about associations, when looking at scatter plots and least squares regression lines, they are not implying cause and effect relationships. You need to do a proper experiment to establish that. And I want to take a look at a couple of examples here. In the NBA, there's a strong positive association between the number of turnovers a player has, the number of times they turn the ball over to the opposing team, and the number of points that the player scores. Turnovers, a bad thing. Scoring points, a good thing. So, what does this strong positive association imply? Does it imply that more turnovers causes them to score more points? No, it doesn't. It just means that there's an association between the two. There's a pattern that exists that as players have more turnovers, they also tend to score more points. Could a player improve his total points scoring by turning over the ball more frequently? That actually doesn't even make sense. It seems like they would probably lose more scoring opportunities by turning over the ball more frequently. There's probably another variable out there, and maybe it's how aggressively they play the game. In another example, A study found that people with 2 cars live longer than people who only own 1 car. Owning 3 cars was even better, and so on. So there is a significant positive association or correlation between the number of cars and the length of somebody's life. So, does that tell us that there's an association between those 2 variables? Yes, it does tell us there's an association between those 2 variables. Does it imply that there's a causal relationship there? Absolutely not. There is probably some other variable, like income, that is causing that association. So, more income, better health care, they tend to live longer. More income, more cars, and so on. Sadly, we've come to the end of chapter 3, and there are some important things at the end of this activity that are universal throughout chapter 3. And I would like you to take a few minutes and read these. Pause the video and read them. And if you have any questions on them, make sure that you ask your teacher.